Hi folks, here is a shortish, hopefully, video on how to determine the charge of an amino acid or a short peptide at a given pH. I'm going to try and do this in one take, so please excuse if I make any errors or little hiccups, which I'll try and correct as I go along. You can see on the slide here behind me, I have a few different depictions of peptides shown here, and this is something that I talk about often with students, is getting used to displaying or representing your peptide in different ways depending on what it is that you were trying to do. So at the top we can see that the side chains are shown in a lot of detail. We can see an abbreviated side chains shown in the second option, and then it's like even more abbreviated and less detail as we go down. So you want to consider what type of representation is going to work best for you as we're going through. Sometimes I use entire structures, and sometimes I will use a very abbreviated way to draw out the amino acids and peptides. Now, if you are doing something like this in an assessment, it's going to be really important that you read the question. If you are asked to draw a structure at any point, that is not really ambiguous. Somebody is looking for the entire structure if that is the case. So don't do anything abbreviated in those instances. However, if you were being asked to determine what is the charge here, then you can use your abbreviated versions, whatever works for you. The other thing that I want to mention is we're going to do some pretty simple examples here, just to keep it easy, keep it nice and high level. You can, of course, determine partial charges on amino acids and peptides and so on, but we're going to stay away from those examples just for the purposes of this video. So I'm going to attempt to seamlessly draw on these slides, and hopefully it'll work out for us. So we're going to dive right into our examples. And for these slides, I've included some resources that you may find useful to have at hand, at least initially, when you are practicing these examples. So our first one, draw all the ionizable forms of glutamic acid or glutamate. So we're going to start by drawing out glutamate. And you may want to start with a structure table, right? If that's where you need to start, but many of you may know the structures by heart at this stage, which is good. So we'll start by drawing our glutamate here. I tend to not draw in the lonely hydrogen up there, okay? So here we go, here's glutamate. Now this doesn't actually ever exist physiologically, right? Because your, if you can see my cursor here, your NH2 in solution in an aqueous environment is never going to exist at the same time as your protonated carboxylate groups. Okay, so typically whenever I initially draw my amino acids or peptides, I will always draw them in their fully protonated states. And so this would not be NH2, but would in fact be NH3 plus. Okay, now if I want to draw all of the ionizable forms, all of them, then I'm going to start by drawing it at, say, a super low pH, so pH equal to 1. At a pH of 1, you've got really low pH, very acidic environment, meaning lots of protons present, and this is going to be fully protonated, meaning that your carboxylate groups will be protonated and your amino group will be protonated, which gives it a positive 1 charge. Now, how you determine that is by looking at the pKa tables over here. Okay, so what we can see here is if we look for glutamate or glutamic acid, the pKa's are going to be listed here. The first two, and I'm going to take a little bit more time here for this first example, but we'll move more quickly through the next examples. But the two pKa's here, and if I jump out of this, let's keep our annotations. I just want to change the color of my pen for this to draw in my pKa's. The pKa's for the alpha groups, if I can see here, alpha carboxylate and alpha amino, for glutamate it's 2.19 for this, 2.19. For my amino group is going to be 9.67. And then for my OR group, carboxylate group, if I look over here, it's going to be 4.25. So when the pH is below that, everything here is going to be protonated, okay? And so my charge there is going to be an overall +1, okay? So we're going to deprotonate this one at a time. So let's go back to our red color to draw the next form. So when you're deprotonating an amino acid, you're just going to knock the protons off one by one in order of their pKa's. In terms of how this happens physiologically or in solution, what would need to happen with the pH is that the pH would need to rise above the first pKa. So if this is 2.19, let's say a pKa of like 3. So our pH rather of 3. And so at a pH of 3, we have our alpha carbon here. Your alpha amino is still going to be positively charged. Your alpha carboxylate group now is not going to be protonated because the pH is higher than that. So it's going to be deprotonated. And then your R group, carboxylate group, will still be protonated because the pKa, if we review that over here, the pKa is still above the pH that we have. Okay, so the next form we have, and let's write in our charge here. So that's going to be, if we just balance our charges here, so that's going to be a net charge of 0. Okay. Okay, let's draw out our next form. Our next pKa up, if I'm looking at the pKa's, this was my lowest. This is my next group that's going to be deprotonated. So at around about pH 7, let's say, physiological pH, we've got, again, we've got NH3 plus, COO, excuse me, alpha carbon, COO minus, okay, because this will still be deprotonated. My handwriting is deteriorating, apologies. COO minus. So now we have 2 negative charges, okay? And so we said this was pH equal to around about 7. And so what we can see here is that we now have 2 negative charges and a positive charge. So overall, our pKa, our charge at pH of 7 is going to be -1, okay? And then finally, if we want to deprotonate past this, if we want to deprotonate this alpha amino group, we're going to have to look at what the pKa is here. I'm going to need to go north of this pH, right? So let's say pH 10 wouldn't even fully do it, to be honest. So let's just say pH 11. So we'll go back to red. So at pH equal to 11, we would have our, this would be, okay? And so we are deprotonated now at the alpha amino group, and we still remain deprotonated at these 2 other groups, which means that overall I have a charge of -2. Okay, so we've drawn, so glutamate, it has 3 ionizable groups, meaning that it has 4 different ionizable forms, okay, because you've got fully protonated and then fully deprotonated, and then your 2 in between. There are shortcuts to doing things like this, folks. You should be aware, especially if you were being asked, the following examples that we're going to do are going to ask us to determine the charge of amino acids and then a peptide at closer to a physiological pH. Let's look real quick at this before we move on. Your alpha groups over here, the alpha carboxylate groups are all acid groups. All their pKa's are really low, right? 1s and 2s. The alpha amino groups, correspondingly, they're basic groups, right? They're all pretty high. The high 8s there is the lowest they get, and then they're up in the 9s and even into 10, okay? Because they're basic groups. And so you can use that to know, even if you don't know the exact pKa, you can estimate it. And, you know, by all means, use your pKa tables as references if you need to. And then you will want to pay a little bit more attention to what's going on in the OR group. Also, just a note here, as you can see, not all of your amino acids have OR group pKa's, right? Because not all of them have ionizable side chains. So the only ones listed, those are the only ones that you need to concern yourself with when you're determining charge of the OR groups. The table below here shows the specific OR groups that can be ionized and also where they can be ionized. So they're shown here, protonated, and what the charge on them will be when they're protonated. Notice that the nitrogen-containing groups, when protonated, are all positively charged. Okay, the hydroxyl group and the carboxylate groups, when protonated, have no charge. And that is going to be something that you will need to know. We don't want to just have an association that, oh, protonation means no charge. It doesn't always. For an amino group, protonation means charged. Okay, so let's dive on to the next one. So we may go a little bit more quickly through these. This will just require one drawing, okay, although I may edit it as I draw it. So the net charge of lysine at pH 7. So I'm going to start by drawing, and you can see my depictions are not like, you know, they're pretty simplistic, and that's fine. So let's say so this is around about a physiological pH, right? So I'm pretty confident that drawing my backbone like this is fine. And now I'm going to put in my OR group here. So for lysine, it's got a hydrocarbon chain. Perhaps I should have picked something a little shorter. And then we've got a nitrogen group here. So this is the unprotonated form, but at pH 7.5, quick check at lysine, the OR group pKa over here is 10.53, which means that this is definitely going to be at pH 7.5, that's definitely going to be protonated, so it won't be NH2, it'll be NH3 plus, okay? So when the pH is below the pKa, below pH, what does low pH mean? It means lots of protons. If there are more protons around, they're going to be more likely to stick to your molecule. That's a simplistic way of viewing it, but it will let you know, it will just remind you, more protons in solution means more protons sticking to your molecule. So we've got 2 positive charges here, 1 negative charge, giving us an overall charge of +1. Okay. Sometimes I will do a shortcut of this, by the way, where I'll just draw, I'll write, here's my shortcut, my abbreviated version. I will write the name of the 3-letter code in the middle, and then I will just write the groups, the ionizable groups. And then this is my OR group, which has, right, so this would be an abbreviated way of drawing this. And so this tends to make a uniform structure out of every single amino acid that you might do this exercise with, which is nice. But you do, you know, to be honest, it's never a bad thing to get practice drawing out the full structures of your amino acids. Okay, histidine. So histidine is definitely one of the fun ones, right? So the net charge of histidine at pH 8.5. So we'll start by drawing out the full structure, right? So we've got our alpha carbon. Again, it's going to be physiological pH, so I'm pretty confident without even looking that my groups here are going to be plus and negative. And now let's draw our, okay, there we go. So at pH, so I need to check, so this here is my group that can be, it's my ionizable group, okay? So at least when you're doing this initially, you should probably just take the opportunity to double check, you know, a table or something to see how is this OR group going to be ionized. Some of you may want to put like an extra hydrogen on over here or whatever. So it is this nitrogen that will be ionized. And if we check our table down here in the lower right, you can see that NH plus, you can see over here, is going to be our ionizable form. So at pH 6.5, that pH, the pH here, 7.5, is above that. So what does that mean here? If your pH is above it, it means that this will be deprotonated. So we've got no charge here. Okay? So overall my charge here is going to be 0. If I was drawing this at a lower pH, below the OR group pKa, which is, where is histidine? On my side chain, histidine is here, pH 6, or down here, it's here, right? So if I'm drawing it below a pH of 6, then this group would be ionized. Okay, one more before we do a peptide. Oh no, we're going straight into the peptide. Apparently I'm racing through this. So what is the net charge of the following peptide at pH 5? Okay, now I am going to draw an abbreviated backbone for this. I'm going to draw one of the abbreviated examples. You can totally draw full structures, and again, as I said, it's never a bad thing to practice drawing your amino acid structures. And if you are asked to draw structures, please make sure you do that. So how I would draw this out first would be my N terminus, and it's at pH 5, so I'm going to go ahead and assume that this will be protonated. I've got lysine, phenylalanine, cysteine, serine, aspartic acid. This is a long peptide, histidine, alanine. So the only alpha groups that I need to concern myself with for a peptide are the first one and the last one. The first, the lysine's alpha amino group and alanine's alpha carboxylate group. All of the rest are busy. They are busy with peptide bonds, so you don't need to concern yourself with those. Now let's think about the OR groups that are going to be involved. So does lysine have an ionizable side chain? Yes, it does. It has an amino group, as we saw, and so if we want to just take a quick look, so this is going to be an NH3 plus, and so you may, at least initially, I think it's not a bad idea to just double check your structures as you're doing this, but the more you do, the more confidence that you'll get. Now when I'm going through this, phenylalanine does not have acid-base chemistry in its side chain, so I just leave it like this. I don't draw anything in here. Okay, so cysteine is going to be up next, and so this has an OR group that has a thiol on it, and the let's highlight my pKa's here. Let's see, cysteine is 8.4, and so again at 8.4, that pKa of this group is well above my pH of 5, so this will be protonated. The next one is going to be serine, which I can pretty much ignore. Aspartic acid, so this is going to have an acidic group. And so this has a group of a pKa of 3.9. And so 3.9 is below, the pKa is below the pH that I have, meaning that this group will be deprotonated. Then we have histidine, which we just saw. And here's an abbreviated way to draw histidine, right? So this time, in the previous example, recall that we were drawing histidine at pH 7. So its OR group was deprotonated, but this time we're drawing its OR group at a pH of 5. The histidine pKa for its OR group is 6, okay? And if you look at it here, what that means is we've got an NH+. So that's a little different from what we saw before. And then we've got alanine, which has no acid-base chemistry, so again, I'm going to ignore that. And now that we have this drawn out, we can simply add up the charges, okay? So we've got plus, plus, minus, minus, and then 1 plus here. So you've got 3 pluses and 2 minuses. So your overall charge is going to be +1. Okay? And that is that. So hopefully that's helpful. The key thing here is going to be practice, folks. Just do as many as you can. Okay? That's it.